Audio Jungle. Audio Jungle.
Hello everyone, myself Narendra Singh Maurya. So guys, today we'll solve Jet Propulsion Gate 2018 problems. Alright, so this is problem number 18 we have here. The first law of thermodynamics is also known as conservation of. Alright, option A mass, momentum, option B momentum, option C energy, option D species. So you know all like first law of thermodynamics. Okay, first law of thermodynamics, as we know, is very basic only. So it is explained for like a cycle and it is for the process. Yes or no? So for the cycle, like suppose this is the system here. Okay, this is the system, and here surrounding, no? And this is what boundary. So suppose if you talk about the cycle, so from surrounding you are suppose supplying heat here, okay, and this system is what doing work. So for the cycle, whatever the amount of the heat you have supplied, that will be converting into work. Okay, and obviously one constant you may get, okay, because it denotes like heat conversion into work or one work conversion into heat. That both will be possible. Both conversion means from heat to work or work to heat you can get. So summation of amount of the heat supplying to a system will be converting into work. This is for the cycle. But the same thing, if you talk about the process, so in the system, your like energy, which is called internal energy, that will be the stored energy. Okay, stored energy. So that will be del U. So whatever the amount of heat you will give, first system will absorb heat, okay, and it will stored, and then it will do work. That is simultaneous. But once you supply heat, it will be converting like work, but at the same time, it will be stored some amount of the heat, which is called stored energy. So for the process, so here for the process, del Q is equal to delta U plus del W. This is for process. So both cases here, what you are talking about the energy or not? Like heat is the energy, work is the form of energy, internal energy, stored energy. So basically, first law of thermodynamics is also known as conservation of energy. Understood? So what is the correct answer? Answer is C. I hope you understood this. All right, next. Now this is problem number 19. In an ideal gas turbine cycle, the expansion in turbine is represented by option A. Okay, I will write all the process so that you can understand. Okay, what is the mean of isenthalpic? Isenthalpic process means H means enthalpy constant. Okay, isentropic. Isentropic process, which is also called reversible adiabatic. In this, S. S means entropy constant. Next, isobaric, which means constant pressure. Okay. Next is isochoric, means constant volume. Now we have a expansion in turbine. So where expansion will take place? In turbine. It is clearly mentioned. No? See? Expansion always takes place in gas turbine engine. Expansion will always take place in turbine. And where compression will takes place? Compression will takes place in compression. Where combustion chamber will where combustion will takes place in combustion chamber. That you all know. So now check basically this is the PV plot. Okay. So 1 to 2 it is compression. Check, this is the volume and this is what pressure. Pressure is rising and volume is decreasing. So this is what compression. So this compression is what isentropic because it is ideal. No? So for ideal case this is the compression. Okay, so I must write here compression because pressure is rising and volume is decreasing. So that is the compression. Where compression will take place, I told you in which component? Compression. Then 2 to 3 we are adding heat. Okay, so where we are adding heat? We are adding heat at constant pressure. Constant pressure means isobaric. Okay, this is isentropic, this is isobaric, and where it is? It is in combustion chamber. All right. 3 to 4. Check, pressure is decreasing, volume is increasing, which is called isentropic. And where isentropics occurs, where expansion occurs in turbine. So for ideal Brayton cycle means it is for gas turbine cycle. Okay. So for gas turbine cycle, Brayton cycle, ideal Brayton cycle, this is the ideal Brayton cycle. So expansion occurs in turbine, and what is the process in expansion? It is isentropic process. So always remember, okay, if I will draw this diagram like here, better here I will draw in short. Check. So 1 to 2, this is entering flow, which is point A. This is 1, compressor is 2, this is turbine combustion chamber, and this is what 4, and this is what exit. So 2 to 3 is the combustion chamber. Take 2 to 3 is combustion chamber. We are adding heat. See 2 to 3 at constant pressure line. I hope you all got the answer. So always remember compression and expansion takes place for the ideal cycle. I am telling always takes place in isentropic process. Combustion chamber heat addition and heat rejection will always takes place in isobaric process. So isobaric process you have to say in combustion chamber. Combustion always occurs in isobaric process, and compression and expansion in compressor and turbine respectively will be isentropic process. I hope you understood. Clearly here you can get the answer. So what is the correct answer? In an isentropic process. So your answer will be option B. All right. Okay. Check 3 to 4. See, this 3 to 4 is what isentropic process. Check. This is what entropy and this is what temperature. TS plot. The entropy is what, constant or not? The constant entropy is called isentropic. Here I have given, check. Constant entropy means what? Constant entropy means isentropic process. So what is the answer? Your answer is nothing but tropic. All right, we'll go for next question. Check. This is the next problem. Okay. Problem number 24. The stagnation pressure at the inlet and exit of subsonic intake are 100 kPa and 98 kPa. 100 kPa and 98 kPa. Remember, this is the subsonic intake. We have two types of intake, subsonic and supersonic. If you talk about supersonic intake, so we'll talk about the shock formation. Okay. Losses will be there because of the shock formation also. So that is the another case of study. That's the reason I have given this stress here. It is subsonic intake. All right. Inlet and exit. So inlet and exit stagnation pressure they have given 100 kPa and 98 kPa respectively. The pressure recovery of this intake will be accurate to 2 decimal places. All right. Check, this is what the intake. I told you many times, this is what compressor, symbolic diagram, this is turbine. Yes or no? So here this point is what? A, this point is 1, this point is 2, this point is 3, this is 4, and this is exit. Very simple notation: compressor, combustion chamber, turbine. Yes or no? So intake, this is what? All the points you know. Yes or no? This is what? Intake, compressor, combustion chamber, turbine, and nozzle. That you know. Check. So I'm considering that part A21. So A21 is intake. Check. This is A. This is 1. At intake, inlet of subsonic intake, inlet. What is the total pressure they have given? Total pressure at inlet. Inlet is nothing but A. So what is the total pressure? P naught A means P naught A. This value they have given how much? 100 kPa. Exit of subsonic. Where is the exit? 1. So what is the total value? P naught 1 means this value. How much they have given? 98 kPa. Yes or no? They are asking pressure recovery of this intake will be. So write the formula for subsonic. The direct formula only. For subsonic intake, or diffuser, pressure recovery, or also called pressure recovery factor. That meaning is same. So factor you always know it is unitless, dimensionless. Na? It is denoted by pressure recovery factor of intake. I must write. It is pressure recovery factor. What is this value? It is nothing but total pressure or stagnation pressure. Total pressure or stagnation pressure. Stagnation pressure at exit of inlet divided by stagnation pressure at entry. No? Here it is given. Check at inlet of intake. At exit of inlet not. Let me correct this. Exit of intake. Exit of intake. Stagnation pressure at inlet of intake, or you can write diffuser also. There should not be anything. What is the stagnation pressure at exit of intake? It is P naught 1 as per diagram. P naught 1 divided by P naught A. Exit by intake of diffuser. All right. So it is nothing but P naught 1 is 98. So this pressure recovery factor, or you just say only pressure recovery, that is also true, is nothing but 0.98. No dimension, no unit, no, because it's a ratio. What is the correct answer? 0.98. I hope you understood this. All right, done. We'll go for next problem. Okay. This is problem number 25. Here they have given a combustor is operating with fuel air ratio of 0.03. If the stoichiometric fuel air ratio of the fuel used to 0.06, the equivalence ratio of the combustor will be. Again, this is formula based problem. The stoichiometric fuel air ratio is the ideal fuel air ratio. Okay. Ideal fuel ratio means what? Means what should be the proper composition of air and fuel so that proper mix. After proper mixing, there the 100% burning of the fuel, because sometimes if mixing is not proper, composition is not proper, like maybe oxygen amount is more compared to fuel, so that is not a proper mix, proper composition. So that time there will not be a proper combustion. So few particles of the fuel will not be burned. It will be unburned particles, and it will go through the uh, nozzle, and it will go for the it will be the wastage part actually, because it is unburnt fuel, and it is passing simply through the air. With the help of air, it is passing through the nozzles actually. Hope you understood what it might mean. So stoichiometric fuel air ratio means there should be a proper composition, proper composition of the fuel and air, so it becomes ideal actually, so that all the 100% fuel particles will be burnt. Hope you understood this. Okay, so I'll write this. They have given fuel to air, no? Fuel to air ratio for the combustor. Okay, for the combustor, check. Okay, this is what m dot a, and this is what combustion chamber, compressor, combustion chamber, and turbine. So here we are adding fuel, m dot a plus m dot a. Okay, so fuel to air ratio means m dot f divided by m dot a. It is also f by a, you can write, is given how much? 0.03. But for the same engine, we have for the same combustor. Okay, this is the combustion system, this is the combustor. Okay, combustor or combustion chamber. So for the same combustor, we have another fuel to air ratio, but this is what? Ideal. I told you what is the mean of ideal. Ideal means there is the proper combustion, 100% fuel particles should burn, so that that should be appropriate composition, and that appropriate composition of air and fuel will be called as a stoichiometric. Okay, it is called stoichiometric or ideal. Okay, stoichiometric fuel air ratio, which is nothing but 0.06. Yes or no? So here they have given equivalence ratio of the combustor. So equivalence ratio of the combustor. It is denoted by equivalence ratio. It is denoted by phi. In many books, it is given by phi. What is the phi? So phi is nothing but fuel air ratio actual divided by fuel air ratio ideal. Stoichiometric, no? ST. So what is the phi? Check. What is the actual? This value is actual. See, they have the combustor is operating. So operating means operational condition is what always actual is real. All right. So that's the reason they have given operating. Operating means actual, real, no? Okay. So it is actual. So it is given 0.03 divided by 0.06. What is the value of phi? Can calculate. Huh? It is 3 by 6, 1 by 2. Equivalence ratio is 0.5, or you can say in percentage it is 50%. Okay. Anyway, so they are not asking value in percentage, they are asking accurate to 2 decimal. So it is nothing but 0.5. This is your answer. I hope you understood. No? All right, we'll go for next question. Okay, this is problem number 32. What they are saying, an aircraft with a turbojet. So we have turbojet. This is turbojet engine. We have flow here, compressor, turbine, combustion chamber. Yes or no? CC. And yes, this is what? Diffuser. This is what? Nozzle. Hmm? This is what? Compressor. Okay. This is what? Combustor. Combustor or combustion. This is what? Turbine. That you know very well. Here we have exit. Exit, and this is the VI or V infinity. All right. So the engine flies at velocity 100 meter per second. So here 100 meter per second, this velocity they have given. If the jet exhaust velocity is 500, what is the jet exhaust velocity? 300 meter per second, which is nothing but, yes or no? 300 meter per second. The propulsion efficiency of the engine assuming negligible fuel to air ratio. Okay, fuel to air ratio, or m dot f by m dot a, they said it is negligible. Fuel to air ratio, they said it is negligible. So small f means this is f by a. Small f means fuel to air ratio, it is negligible means approximate to 0. So if fuel to air ratio is what negligible, then what is the propulsive efficiency? I will give one short formula, 2 alpha divided by 1 plus alpha, where what is the alpha? Alpha is V infinity by Vj or Vi by V exit. J for jet velocity, E for exit, so same thing. No? Vi by V infinity. So what is the eta P? This is the propulsive efficiency, okay? Always remember this is very short formula. Propulsive efficiency. Eta P. 2 alpha divided by 1 plus S. 2 alpha. What is the alpha? Vi by V exit divided by 1 plus Vi by V exit. 2 into what is the Vi inlet velocity? How much? 100 is given. So it is 100 divided by 300. Yes or no? We can calculate this. It is 2 by 3 divided by 4 by 3, I think. How much you may get? 1 by 2. What is value? 0.5. In percentage, it is 3%. Check. Option B. Simple one only. It's formula based. Simple you can calculate. What is the correct answer? Option B. Now, next question. Problem number 33. Okay. One more thing I will suggest you remember this formula. This is a very frequent formula, and anytime they have asked question based on this propulsive efficiency for jet engine. 2 alpha by 1 plus alpha, where alpha is nothing but this value. Very important. Very important. Okay. This is problem number 33. An aircraft with turboprop. Okay, first turboprop question they have asked. Anyway, turboprop. Engine produces a thrust of 500 Newton and flies at 100 meter per second. All right. If the propeller efficiency is 0.5, the shaft power produced by the engine. All right. So, check. Okay. This is what turboprop. All right. All right. So this is what propeller. Hmm? Anyway, you just give me time, so I will correct this. This should okay. Now it is fine. Now it is fine. That black line I had given for my convenience, but it's okay. Now check. So whatever this is what propeller. Okay, this is what propeller. This is the reduction gear or gear mechanism. You can say. Okay. Rest this is nothing but compressor, combustion chamber, and turbine as usual. All right. So this propeller efficiency they have given to you, and in fact they have given engine produces thrust of 500 Newton. What is the thrust produced? 500 Newton. It is flying. Okay, it is flying with what velocity? 100 meter per second. So that is VI they have given. This propeller efficiency they have given eta P. Propeller I will write PR because eta P if I write then it will be propulsive efficiency. So eta PR 0.5 they have. They are asking what is the shaft power. Obviously shaft power will come because through the shaft propeller is what rotating propeller and this uh, gas gas generator means compressor, combustion chamber, and turbine. So that propeller is what connected with the shaft. All right. So definitely shaft power will come into picture. All right. Now they are asking what is the shaft power produced by the engine. So here because propeller efficiency they have given. So propeller efficiency formula, because this is formula based problem only. So I will write propeller efficiency. Propeller efficiency. Simple formula. What is the thrust produced? Thrust power divided by shaft power. Because here through the propeller we are getting 80% thrust, and from here we are getting 20% thrust. Approximation I am telling you. So more and more thrust you are getting with the help of propeller. Okay, very less amount of the thrust you are getting from the you know through the uh, exhaust jet. Most of thrust you are getting from the propeller. All right, due to reaction force, uh, you may get thrust. Okay, from the propeller reaction based principle. So this is the thrust power divided by shaft power. So what is the shaft power here? This is the formula. Okay, this is the remark point. You need to remember this. Very important. So what is the shaft power? Shaft power will be divided by eta PR, propeller efficiency. What is the thrust power? Thrust into velocity divided by eta PR. So shaft power is nothing but thrust. How much they have given? 500, velocity 100. Eta PR, it is given 0.5. So this is the formula. So nothing is here to like to get confused, because it's a very simple formula. If you know, then all the data they have given. Okay, so you can solve this in calculator. Wait, 500 into 100 divide by zero point 0.5. Okay, it is nothing but 100, no, 100 kilowatt. Check any option is there. 100 kilowatt B. So here this is nothing but, because it's a power, it's a 100 kilowatt shaft power. So what is the correct answer? Answer is, check, B, 100 kilowatt. Simple formula based. All right, direct formula you need to remember. You need to remember this formula. I suggest to all, please remember this formula. Important. Okay, for the propeller. All right, so these are the questions they had asked in gate 18. Okay. All right, so like the video, subscribe the channel those who are new, so that you will get notification for next video also. All right, do very hard work, study well. Thank you all. Thanks so much.